Thank you. So I come from Exxon Research as well, where I work in seismic software and seismic interpretation systems. And so hopefully my goal here is that at the end of this talk, you'll run out of here with what I'm going to show you, trying to reproduce this in your own facility. And maybe buy a few GPUs along the way. So I love this chart because this comes from Total, and this gives me job security. In fact, all people in this room have job security. This is the roadmap for the oil and gas industry. So it's basically showing compute requirements on the y-axis and over time. And Jack Wells just presented and said that Jaguar was 1.7 petaflops, so that's right around here, and Titan is 27 petaflops. So what we're showing on the chart here are different algorithms that are being used in industry today. Reverse time migration is here, and there's well over 50,000 GPUs in production today. FWI is also in production. Really what you have with FWI is iterative RTM. You just run that over and over and over. The focus for my talk is around elastic, not imaging, but wave propagation. Elastic imaging is really going to require yet another step change, and we're working with that in our next generation GPUs to allow that. But modeling is important for people that are doing, say, collecting data, acquiring data. It can cost over $200 million to acquire one survey. And if you can save 10% by not acquiring 10% of that data, that would be $20 million, and you can buy a pretty decent cluster with that. And the way you get there is by running simulations. So what I'm showing, we're going to talk about today is how to run these simulations using OpenACC directives. A lot of the codes that are running in production are using the CUDA runtime, but there are capabilities to use the directives, as I'll show you in a minute. Also, for the oil and gas industry, it's not just seismic imaging where we're seeing benefit with directives. There's reservoir simulation with billion-cell models, and there's a national oil company that has really, really, really large models, and they're using OpenACC directives. Also, electromagnetic, controlled source electromagnetism, a company called EMGS that owns this space, presented at GTC a year ago, and they talked about their experiences with OpenACC directives. So it's across our workflow, it's not just seismic imaging. Okay, so question, why use OpenACC for elastic wave propagation? The Earth, after all, is inhomogeneous, and it does deform when you send signals through. Well, I'll show you the steps that we went through to get a 7x speed up on a representative code. And the person that was working on it, Matt Colgrove, couldn't be here. He was, I think, going to present this. But he's got a good understanding and knowledge of underlying infrastructure. He was able to do that in 5 hours. Your mileage may vary. But let's focus on the 7x performance uplift. If I can run 7 times more iterations, I can have a higher degree of confidence of my model. I have a higher degree of confidence in my model. We're working with multi-million-dollar projects. You don't want to drill a dry hole. So this is the reason why a performance uplift is important. But it's also, we're hearing time and again to make this easier and also make it portable for other accelerators. I want to make one change, and then I have the compiler direct that to an NVIDIA GPU or an AMD APU or an Intel 5, whatever the case may be. And then also make it so that the domain experts can get a reasonable benefit from these GPUs. Do faster iterations, make it accessible without having to know all the lower level details. So the question is, how do they work? How do compiler directives work? First, start with a multi-core host. This happens to be a Cray CS Storm, recently announced, has up to 8 GPUs. On the right is just a cartoon of what's inside a dual socket Intel platform with various connection mechanisms. And you just add GPUs. So you put a tray in, you can have up to 8 GPUs in one server. Sometimes, some of our GPUs have actually 2 chips on the same board. We have in production seismic companies that are doing RTM processing with 16 GPUs in one server. This is the home of big data. And if they can keep the data on the system without having to distribute it, that's a win. It's a saving and programming effort. And that's an important thing for this community. If you look at this picture, that looks like a pretty small pipe, that PCI Express slot, feeding multiple GPUs. The point is that you can overlap communication with computation. It's inherent in the model, and OpenACC is evolving that with an async clause to allow that to happen. It's an area where we need to continue to grow and mature. But there's other ways to skin this cat, and you'll see in my case study. So you've seen this slide. I'm just going to re-emphasize that we are going to talk about OpenACC directives today. But you can use the directives in cooperation with libraries and in cooperation with languages that are native to you that have been extended to be able to use GPU technology. So, for instance, an FFT library is highly tuned by NVIDIA employees, or they know the architecture better than anything else. The best code you write is the code you don't write. And if you can depend on a library, that's a good thing. And there may be some portions of your code where you might need to do something that's specific on the GPU. You can use the compiler, like a C or a C++, CUDA Fortran, Python. You can even say MATLAB, if you like, to allow you to interoperate with certain portions of your code. Can use directives, other portions can use native languages. Try to minimize what you have to port. So how does this work as well? So you have, again, CPU works in complementary to the GPU. All the serial code running on CPU, and you have some nested loops. So you insert a directive around that nested loop, and the compiler and the runtime do the following. So they'll generate the parallel code, they'll allocate and transfer the data to the GPU, they'll execute the kernel on the GPU, and then help bring the data, transfer the data back to the GPU. That's in its most elementary form. We'll find out there's other mechanisms that are involved here. That's just the base level. Questions? Okay. So the rest of the talk is going to be in three main areas. It's primarily to focus around a case study. And that is the 3D seismic elastic wave simulation. And then associated with that case study, use multiple steps you go through to take an application that's running purely on the CPU host only. What it takes, using OpenACC directives so that it runs in a multi-GPU environment. And we're going to use a profile-driven approach. Because these tools, I mean, they're inexpensive, and they provide some pretty amazing capability. You ought to have it in your bag so that that can help you. And using a profile-driven approach is the way to go. And I'll summarize it. So first, the 3D elastic wave simulation. So, okay, the animation that you see here, I'll talk about in a minute. But what I want to focus your attention on is the code is called Seismic CPML. It's convolutional perfect matched layer. It's written by Dimitri, Komatitsch, and Roland Martin. They're actually at they're in a French institution now. At the time they wrote this, they were at the University of Pau in France. They are Gordon Bell Prize winners, 2006. That's, if you don't know, that's one of the highest honors you can get in HPC communities. That's what they're doing. And they posted this code. There's 10 Fortran modules out on the web. You can download them. You can learn from a Gordon Bell Prize winner. What's the real science is, where does the geoscientist want to focus its attention? On the application domain. Try not to get bogged down in the lower level details. And the main reason for developing the code that they developed was to study the effects of the absorbing layer. When you, in the depiction here, the plus sign is the source. So the code, the standalone Fortran code, has a mechanism to inject a source, and then it has two receivers, the green squares. And you're basically, when waves are propagating in the Earth, they deform. The Earth is elastic, and as computer scientists, we have to put a grid around it. We put a grid around things that has effects of boundaries. And the question is, how do I deal with this boundary, especially if I got a source that's close to the edge of the survey, or if I have a really long distance between my source and my receivers. This causes bigger effects around grazing incidents causing spurious reflections. And so the formulation underneath of this is you want to simulate waves traveling through the Earth. And you want to simulate them in an inhomogeneous or elastic fashion. And so they use Maxwell's equations with a velocity stress formulation. It goes to show, the reason I put the grid there is because there's approximations in all of the seismic imaging codes today. And it just happens to deal with how many properties at each grid point are you able to operate on. And it makes some simplifying assumptions like velocity and the vertical is 0. You can not have to carry as many properties, making the problem easier. But they don't want to make the problem easier, as you saw with the roadmap. They want to model the real world. Well, but I've worked with Matt Colgrove at PGI, now NVIDIA. Some of you may not know that PGI is part of NVIDIA. Anyway, I showed him this code, and Matt took it and ran with it. He actually picked the 3D isotropic code, and it's using a second-order spatial operator. There's also a fourth-order viscoelastic operator. That's going to do even more computation, should scale even better, because the more compute you have, the better things are. So there's a link here, and I have a references page at the very end so that you can, at the end of this, go home and download this. Try this yourself, because there's step-by-step instructions of where we're going to go to next. Okay, so that's the application domain. If you look at the computation domain, the computer scientists, some companies organize themselves where I just have an app domain, I just have geophysicists, and they just work on that. And then they hand it off to the computational team, and they work on making things run fast. It's rare to find somebody that has the combination of the two. But this is the world that we live in. It's 3D finite difference approach is very common. There's also finite element. Finite difference is used all over the place. It's a way to approximate derivatives. And the University of Houston has a really good test case showing heat conduction. Transfer heat from one medium to the next. Put a grid around it, do some derivatives, you put a finite difference. It's up on the openacc.org website. Really good. Sunita was one of the authors. It's an excellent example that you can extend this to go across multi-GPU. It's really nice. But it's using OpenACC directives. So that's what's common in here. There's a discretization in the second and fourth order space. I talked about that already. Dimitri and team are using a staggered grid to help save on space. Space is a premium as you're gridding these things up. So this is a reasonable test case, right? Now, the key here is it's also using MPI, non-blocking MPI, to do the domain partitioning. And that's on the subdomains. The inner regions are using OpenMP. This is what you get for free when you download this thing. It already is parallel. It's written in Fortran. So, here's what he does. He takes a volume, and he divides the volume into Z dimension so that you have subcubes. When you do that division, you have to put a halo around so that you can do carry the calculations from one neighbor to the next. You may have some padding and halo data. Okay, it's all in the source code. He's doing an MPI sends and receives the domain decompose the data. What you want to do is start that computation on the halo or in the padded areas first, and then kick those off. So you're transferring the data. At the same time, you can now then start working on the inner region. So you can overlap computation with communication as long as that inner region is big enough that you spend enough time computing on that inner region to hide the latency of any of the communication. And the communication goes across PCI Express or across networks, and InfiniBand connected machines are in production with this. Okay, so that's the kind of the. This is all part of this Seismic CPML case that you can download. One source file, 3D isotropic, has all of those, all the features that I just described. First thing you do, get a system that's reasonable and compile, and you turn on, get the right MPI implementation, turn on OpenMP, get a baseline. This is great because the other thing it's doing, that image that I showed where you were cycling through the wave propagation, it's actually doing the source injection, and it's every so many time stamps sending a seismogram. So it's actually doing I/O as well. So what you want to do is say, okay, what's my baseline? So run this with on a system that has 8 cores total, and get a baseline of performance. So that's the introduction of the seismic wave equation. Next, I'm going to talk about the profile-driven approach. And this is it. So you start by identifying parallelism, express that parallelism. Sometimes when you express the parallelism, funny things happen, because you try to take the shortcut that forces you to think about data locality. Then you go optimize, and it's just a nice iterative loop iterate until you get done. So first, let's talk about how to identify parallelism. Well, you ask these questions, typically of code, to see. For the seismic CPL 3D isotope case, it's using MPI and OpenMP, so by definition, it's parallel. And in fact, a lot of things in seismic is embarrassingly parallel, because every seismic shot record is independent from the next shot record, from the next shot. Doesn't have nested loops. In this particular case, you're iterating over, in the default, 2,500 time steps. Inside of that loop, there are 8 nested parallel loops. So far, so good. Questions about synchronization, data access, and compute intensity are a little harder to answer first go. But if you're spending enough time computing in the inner region, then you're not going to be worried about synchronization. You're definitely going through a regular grid and regular access. Question is, how do I determine compute intensity? What is compute intensity? It's the ratio of how much time I'm spending computing and how much time I'm transferring data. If there's a tool out there, wouldn't you want that? Wouldn't you want to use it? The PGI has a tool, you just compile with -m-info equal intensity, and you run a representative case. And what we found in this particular case, so the general rule is the parameter that comes out of the compiler, because the compiler and the runtime are good at bookkeeping and keeping track of mundane things that you don't want to have to necessarily bother with. So if the compute intensity is 1 or lower, that's not a good candidate. And that's important too. You don't want to waste time, right? Your productivity. If I can find something that tells me this is where I should work versus not, that's good. If it's 4 or higher, man, that's a really good case. In this case, for the 3D isotropic, it was about a 2.6. Still, could be better, and there's room for possible improvement, but it's definitely worth pursuing and going further. The other thing is the tools help you identify critical regions. There's nice graphical profiles. Even on the craziest storm, from my house, I connect to the system in California, has 8 GPUs. I bring a No Machine X window back to my display, and I can run PG profile, PG collect, and PG profile. And out comes a graphical display that I can see. Yeah, there's time being spent in this particular routine. And it's a little more tricky with MPI because you're collecting data across multiple machines possibly, but there's mechanisms to allow for that as well. Okay, so that's how you identify the parallels. Use the tools that are available there. So once we've identified, yeah, there's good parallelism with this code, what's the next thing you want to do? Express that parallelism. So we find this loop, and this is one of the 8 inner loops. Remember, there's a time step loop, 2,500 times you're going through this, excuse me. And so this looks like a pretty compute-intensive one. I didn't keep all of the logic on here, but this is real code. This is what you would download. Let's go ahead and insert a directive in here. Pi told me I can walk out of here and I just go insert a directive. And parallelize fast. Right? So the question is, I give a little tutorial, a little bit, for those that may not know what the directives are, just to kind of give you a background on this. For C and C++, they're pragmas. For Fortran, they're just a comment. And the syntax is pragma, ACC, and the directive followed by various clauses. We can talk more about the clauses for each one. There's a parallel loop clause. And really what this does is, if you put it above a for loop in C or do loop in Fortran, the compiler will read this and say, I'm going to generate parallel kernel, and the kernel is a function that runs on the GPU. You also have another directive called the kernels, pragma ACC kernels, and you can denote it by a block of code. And in this case, it's going to take these two different for loops and generate two parallel loops and two separate kernels. So the question is, which one do you use, parallel loop versus kernels? Well, a parallel loop that usually requires more analysis by the programmer. Also, parallel loop is more of what you might be accustomed to for OpenMP. Again, I'm trying to make productivity and take what you know and extend it a little bit. Kernel directive, the compiler actually performs the analysis, and you can cover a larger area of the code, and the compiler has additional leeway. Both of them are valid, and both can perform equally well. Now that I inserted that directive in the code, how do I build the code? When you use the compiler and you use a -ACC option, I use it very strict in this case. You don't necessarily have to. And then an important command line option, is -minfo equal Excel. The compiler is really good at bookkeeping. It's a shame if you don't listen to what the compiler is telling you. So turn that switch on so that you can see what's happening behind the scenes and read that data. And this shows on line 1351, which was that code I showed earlier, that the loop is parallelizable. So that's worth it in itself as a total of confirming that, yes, this is parallelizable, helping you not have to do something. It also generates the kernel. I'll talk more about this later. And then the other thing that's interesting is it found a sum reduction, two of them. You see them in the code? So total energy plus a bunch of stuff, total energy kinetically. That's a reduction. Those are typically hard to optimize. And people do this, they optimize it by hand in code, spend hours trying to come up with the best thing. It's nice that the compiler recognized it, and it's nice that it's using the backend to automatically use that reduction. Again, you didn't have to write that code. The compiler did that for you automatically. All right, so now we recompile with that, now we run. And we run with 2 MPI processes, no OMP threads, because we turned off OpenMP. We run on 2 GPUs, and it went 3 times slower. 3 times slower. But that only took 10 minutes. Okay? This is a common problem. People start an experiment, and they say, this is no good, this doesn't work, throw that thing out of here, give up, quit. Remember, there's a reason OpenACC exists, and it's not OpenMP right now. It's because there's an accelerator and there's data movement behind the scenes. So, excessive data movement is the reason that it went slower. You can't just put a directive around the most expensive loops and say, done! But you can go and use profilers. So this is a profile-driven approach. So from within MPI, you can export an environment variable. And on each individual GPU or each individual node, each individual MPI rank, it's going to collect a profile for that rank. And you bring that back into your interactive tools and work on it. PG collect can also be used at this point. And the interesting thing with when you say PGI ACC equal time equal 1, it collects data that's printed like you see here. And it shows that we are in fact going through this loop 2,500 times, and of the total time here, the majority of that time was spent in data movement. It tells you that the compiler, the profiler actually shows this. for you. Some other tools that NVIDIA has is an NVIDIA profiler. Again, with MPI run, you can say nvprof. It's a command line tool. If your application just runs on a command line, you can say nvprof and collect statistics about a running application. In this case, you want to maybe, again, we can go to separate MPI ranks, so you want to collect separate log files. And in this case, this is just an example using Laplace to show you that, whoa, whoops, you know, if we put that compiler directive, the majority of the time it's including a mem copy, sending the data from host to the device, or from the device back to the host. So these tools are available for you to help identify where data movement is part of your profile. Also, you can collect that log file and then bring that into an interactive tool. We have a visual profiler. So this is the run of a Laplace over time. You can see a natural cadence on iterations on loops. And you can drill down in those individual iterations. You're collecting information about what's going on the host, what's going on the GPU. And you can identify if there's opportunities for overlap. Okay, so that's expressing parallelism. Now let's talk about expressing data locality, because we identified putting in that directive to slow down now what you do to accelerate. Okay, so this is an example of the code where you actually put some data directives in the code to get the acceleration. And I'll talk about what those data directives are here. So there's an ACC data. It basically says arrays within this region will remain on the GPU. But there's also some clauses around those. So I won't read all of this for you, but there's a need to sometimes keep the data on the GPU, copy it down. Sometimes the data is already there, so you just notify that it's present. There's a number of clauses here to handle the scenario to minimize data movement. Also, array shaping is key. There's sizes of the arrays can be dynamic at runtime, so it's important to be able to handle array shaping. And the present clause, it's also scope is important. For instance, you can say in the main that the data for array A needs to be copied to the GPU, and then when you're in that function, you declare it as a present with the right shape values. This is really critical to performance, and it allows you to have a scope that's made bigger than just one file. Okay, so we do the data clauses and making sure that the data stays on the GPU. Also, McKercher took the data and massaged it so that it was sending tiles of data at the same time instead of just one array. Tiled that data to get. Sometimes it's not counting how much you're moving, but how much data you're moving across the PCI Express. So I was able to get a tremendous speed up just by reducing the amount of data movement. And again, you can go back and profile and find out, yes, indeed, I did get better gains. So this optimize, there's levels of parallelism, there's vector, workers, and gains. Primarily what you would focus on is gains and vectors from within the compiler. These are ways that you can adjust to try to take advantage of, say, shared memory or memory accesses so they're coalesced on the GPU. It's a lower level of granularity where you can get finer control to try to get better performance. Matt worked, in this case, he actually interchanged the loop because with a gain, you want to have a high iteration loop count. And actually spent a fair bit of time getting move along here. Spent a fair bit of time, 120 minutes, trying different schedules, and really didn't see that much performance uplift at all. So the default schedule is usually pretty good. But at the end of this, we got a 7x performance uplift after 5 hours of programming effort. Again, very knowledgeable of the underlying architecture. It never hurts to have that knowledge. That makes this easier. I heard the word easy. It's easier if you know that underlying architecture. That's always going to be the case. Okay, so summary. Hopefully you've seen that there's a representative case that's meaningful for where this industry wants to go. Geoscientists are thinking about elastics right now. How can I do this? Take this test case and morph it in and see how it works in your world. There's some interesting ways to domain decompose the data. It's already using OpenMP. Take that out, maybe leave OpenMP in there. Try some different things. You can learn a lot by taking work of others and extending it. And it helps to have really good tools. So I hope at the end of this that you will consider going and trying this yourself. Again, the why directives, we've talked on this a lot already. Single source, abstracts the device details away, rapid development, and low learning curve. It's all about productivity, but it's also about getting performance out of that productivity as well. Here's references. This is on the USB stick so that you can go. This is the actual paper by Matt Colgrove. He has the source you can download. You can go read the paper from there. I also shamelessly borrowed a lot of these slides from Jeff Larkin. He has a great presentation online that you want to learn more about this. Go listen to his presentation. And don't forget the OpenACC work. U of H is doing validation on a lot of these things, and that's really a good partnership. They're doing some really terrific work, and trying to be part of this effort. If you have any questions for me, I don't know if you can see that, but there's my email. And that's on the USB. That's it.